Hi, I'm Mark Barsamian. In this video, I'll be doing examples involving tangent lines and instantaneous velocity. This material is from section 2.5, Basic Differentiation Properties, from the middle of page 151 to the top of page 152, examples 7 and 8. The homework problems include these two problems from section 2.5, but also this material has to do with concepts introduced in section 2.4. In section 2.4, we discussed tangent lines and instantaneous velocity. We didn't do too many exercises or examples in that section because the examples are quite hard when you're using section 2.4 techniques. So let's review some of the background concepts from section 2.4. We had the instantaneous rate of change of a function, which is denoted by this symbol. And we usually talk about the instantaneous rate of change at a particular x value. And it's denoted by this symbol, and it's computed by this formula. And it's just simply the value of the derivative at a particular x value. We learned about this instantaneous rate of change before we really talked about derivatives. But now that we've talked about derivatives, we recognize what instantaneous rate of change at x equals a is. It's the value of the derivative at a particular x value, x equals a. Also in section 2.4, we talked about the tangent line. The line that's tangent to the graph of a function at a particular x value has these two properties. The line contains a particular point, the point of tangency, that has those coordinates, and the line has slope m that's given by this formula, the tangent line slope. And we talked about the idea that since we know those two things about the tangent line, it has a known point and a known slope, it's easy to build the point-slope form of the equation for the tangent line. It's this equation. In section 2.4, we also discussed the terminology of position and velocity. The idea is when you say that an object is moving in one dimension, it means that a single coordinate can keep track of the position of the object. So we have what's called a position function that gives the value of that position coordinate at each time. So in our book, the position function is usually called f, and the variable x is for time. So this symbol f parentheses x means the position of the object at time x. And average velocity of the object was computed by one of these calculations. So in other words, average velocity is the same as what we called average rate of change of a function. And the instantaneous velocity is computed by this formula, which is just simply the instantaneous rate of change of the position function. Notice that the computation of instantaneous rate of change, or velocity, or a tangent line slope involves a derivative. When we discussed these kinds of things back in section 2.4, the only way that we knew how to compute derivatives was using the definition of the derivative, which we did using the four-step process. That was a difficult process, difficult computations. Now that we're in section 2.5, we can compute derivatives more easily using the derivative rules. So this makes problems about instantaneous rate of change and tangent lines and velocity much easier. So that's why we're returning to these kinds of problems now, is because we can study them again without so much computation. So our first example is similar to 2.4 number 15. For this given function, the slope of the graph is known to be 4/5 at the point where x equals 4. And the question is, find the equation for the line tangent to the graph of f of x at that point. To think about how to solve this problem, let's go back up and remember what we know about the tangent line. The tangent line contains this known point, and the tangent line has slope that's this quantity. And the equation for the tangent line is this thing. Let's think about working backwards from what we're asked for. We are asked to find the equation for the line tangent to the graph of f at that point being there. So let's write down for our reference that form of the equation for the tangent line. So we need to build that. So we're going to need to find these three quantities. Let's think about where we might get them. First of all, we're told that the point that we're interested in is x equals 4, because that's where we know something about the slope of the graph, and that's where we need to find the equation for the tangent line. So that x equals 4 is the x-coordinate of the point of tangency. So that tells us that our a, the thing that's going to go at this location in that equation, is x equals 4. So what else do we know? Think about this given information. The slope of the graph is known to be 4/5 at a certain spot where x equals 4. What would that mean in symbols? It would mean that f prime parentheses 4 is 4/5. That's the known slope of the graph at the point where x equals 4. But remember that the slope of the graph also means the slope of the tangent line. So this number, 4/5, is the tangent line slope. So we've now got two of the quantities that we need to populate this equation. We've identified our value of a, it's the number 4. We've identified our value of f prime parentheses a, it's this thing. So that leaves us with this to figure out. Now remember what f parentheses a means. We know what a is. A is 4. So f parentheses a means f parentheses 4. And what that means is to substitute x equals 4 into the formula for f of x. F of x is way up here. That's our formula. So we're going to substitute x equals 4 into that formula. So f parentheses 4 is the number 5. That's the y-coordinate of the point of tangency. So we now have a value for a, it's 4, that's going to go there. We have a value for f prime parentheses a, that's the number 4/5. And we have a value for f of a, it's the number 5. So we have those three quantities that we need to populate that equation, so now we can build the equation for the tangent line. That's our equation for the tangent line, but that's in point-slope form. Let's convert the equation to slope-intercept form by solving for y. So when we solve that equation for y, we get y equals 4/5 x plus 9/5. So there's our equation for the tangent line. Now before going on, I want to go back up and look at the problem statement again. In the problem statement, it was given that the slope is known to be 4/5 at the point where x equals 4. The given information could have been given in a different form. They could have said The instantaneous rate of change is known to be 4/5 at x equals 4, because remember what we observed before when we recalled our definitions of things. The instantaneous rate of change of a function at x equals a is the same as the slope of the line that's tangent to the graph of f at x equals a. I bring that up because you have two problems on your homework that are similar. One is like the one that we just did, where the slope of the graph is given to be a particular value at a particular x value. The other problem has different wording. It has wording like this, where you are told something about a known value of the instantaneous rate of change of the function at a particular x value. So it's the same kind of function, just different wording, just asking you to make that connection that instantaneous rate of change of a function is the same as the slope of the tangent line for that function. All right, let's go on to the next example. Example 2 is similar to a problem from section 2.5. You're given a polynomial function, f of x. We're supposed to find all this stuff. Find f prime, find the slopes of some tangent lines, find some coordinates of points on the graph that are going to have horizontal tangent lines, find equations of tangent lines, or find an equation of a tangent line, and then illustrate the results on a given graph. So let's get started. Now remember my approach to finding derivatives. We start by writing down the symbol for what we're being asked to compute, and then equal sign, and then just the start of the computation is just to write the derivative symbol next to the formula for the function. Our approach is the same as we used in the previous couple of videos. We start by using the sum and constant multiple rule. And the result of that is this expression with 4 separate derivatives, and in all the expressions that had multiplicative constants, the multiplicative constant slips through that derivative symbol. That 3 comes through, that 9 comes through, but that 11 is not a multiplicative constant. It's a constant function, so it gets stuck inside that derivative symbol. All right, now we will use the power rule to find these 3 derivatives. Now for the first term, we have n equals 3. For the second term, we have n equals 2. And for the third term, we have n equals 1. So when we use the power rule, we're going to use those values for n. So here we had the left side of the power rule with n equals 3, and here we have the right side of the power rule. We replaced the left side with the right side. The power rule says we can replace this expression with this expression. So notice the new expression does not have the d over dx symbol. Instead, it has the old exponent pulled down front and the new exponent computed using some arithmetic. The next term in our result is minus 3 times parentheses 2x to the 2 minus 1. So notice that 3 hangs out in front, and the result of this derivative gets put into these parentheses. And again, notice the format. Up here we have what is the left side of the power rule with n equals 2. It has the d over dx symbol, and there's nothing going on, no computations on the left side. On the right side of the power rule, you have an expression that's made up by bringing the old exponent down and putting it in front, and constructing the new exponent using arithmetic. And there's no d over dx symbol on the right side of the power rule. So the power rule says that you can replace this expression with this expression. And finally, the power rule with n equals 1 looks like this. Bring down the exponent in front and then construct the new exponent by lowering the exponent by 1. Now all of those exponents are pretty easy computations, but I don't do them in this line. I do them in the next line. Finally, our last term is an easy derivative. Using the constant function rule, we can see that the derivative of 11 is 0. Now let's clean up, and we get that the derivative is 3x squared minus 6x minus 9. So we've done part A. Now part B, we're supposed to find the slope of the line that's tangent to the graph of f at x equals 3. Now what does that mean? The slope of the line that's tangent to the graph of f at x equals 3. This question is asking you to make a connection. What do you know about the slope of the tangent line? Let's go back up and review the definition of the tangent line. So the tangent line has slope m equals f prime parentheses a. That thing, that's the slope of the tangent line. M equals f prime parentheses a. Back in section 2.4, we had to compute that derivative, f prime parentheses a, using this really hard method of using the definition of the derivative, the four-step process. But now that we're in section 2.5, we can find f prime parentheses a the easy way. So for B, what we're being asked for, finding the slope of the line that's tangent to the graph of f at x equals 3, what we're being asked for is to find f prime parentheses 3. So, again, finding the slope of the line tangent to the graph of f at x equals 3 means we need to find m equals f prime parentheses 3. Now, you have to be careful about reading this kind of symbol. We know that 3 is a number. If we take the derivative of 3, we would get the number 0 because the derivative of a constant is 0. But this symbol is not asking us to take the derivative of 3. It's asking us for something very different. This means that we have to start with the formula for f prime of x and substitute in x equals 3. So we found f prime of x equals 3x squared minus 6x minus 9. So that means that the slope is going to be f prime parentheses 3 obtained by plugging x equals 3 into that formula. So our result is that the slope of the tangent line at x equals 3 is 0. That's the end of part B. Let's go back up and see what we're supposed to do for part C. In part C, we're supposed to find the slope of the tangent line at x equals 0. To find the slope of the tangent line at x equals 0, we should compute m equals f prime parentheses 0. Because remember, this symbol means the slope of the tangent line at the point where x equals 0. So we have our formula for f prime of x, so we're just supposed to plug in x equals 0 into that. So the slope of the tangent line at x equals 0 is this number minus 9. Notice those two results are kind of interesting. The first result tells us that at x equals 3, the slope is 0. The second result tells us that at x equals 0, the slope is negative 9. Let's go on to part D. Find the x-coordinates of all points on the graph that have horizontal tangent lines. Well, remember that a horizontal line has slope m equals 0. But remember how we find the slope of the tangent line. We use the derivative to find the number that's the slope. So let's go back up. At x equals 3, we plugged 3 into the formula for the derivative. We got that the derivative was 0. At x equals 0, we plugged 0 into the derivative, and we got the number that's the slope at x equals 0. So in this problem, we want the slope to be 0. So in other words, we want the value of the derivative to be 0. So we're going to set the derivative function equal to 0 and solve for x. I'm going to turn that around so that I can work down the right side. Now remember how to solve this kind of equation. We factor some more. We see that these two terms tell us the x-coordinates of the places where f prime will be 0. The x equals -1 corresponds to that left factor, and the x equals 3 corresponds to that right factor. So those are the places where the graph has a horizontal tangent line. So that's the answer to part D. Let's go up and recall the question for part E. In part E, we're supposed to find the equation of the line that's tangent to the graph at x equals 2. And we're supposed to show all details and present the final equation in slope-intercept form. Well, remember the approach that I always take. I start by writing down the thing that we are going to build. We need to build the equation for the tangent line now. If you've forgotten, let's go up and have a look at that. Remember, the generic equation for the tangent line is this thing: y minus f of a equals f prime parentheses a times the quantity x minus a. And remember the approach I always take after I write down that equation. I get the parts that we're going to need to populate that equation. So the first part is easy. The value of a is given to us in the problem statement. So we've found the number that's going to go there in that equation. Now, what about this? We need f parentheses a. Now we know the value of a is 2, so that f of a actually means f of 2, and that means substitute x equals 2 into the formula for f of x. Now let's remember what the formula for f of x is. The formula for f of x is this thing: x cubed minus 3x squared minus 9x plus 11. So when I substitute x equals 2 into that formula, I get so our result is that f parentheses a is this number minus 11. That's going to go into that spot in the equation. And remember what that number means. That number is the y-coordinate of the point of tangency. Finally, we need to compute f prime parentheses a. Now that means f prime parentheses 2, because a is the number 2. And remember what that means. That means to substitute x equals 2 into the formula for f prime. Remember that f prime of x was 3x squared minus 6x minus 9. So when we substitute x equals 2 into that formula, we get the following. So the value of f prime parentheses a is the number -9. That's what's going to go into that spot in the equation. And remember the meaning. That's the slope of the tangent line. So we've got the parts. Now we substitute the parts into the equation. Our a equals 2 goes into that spot. Our f of a was the number 11, and that goes into that spot. And finally, our f prime parentheses a was the number -9. That goes into that spot. So in solving these tangent line problems, you have to understand what you're trying to build. You have to understand the approach of getting the parts, and you have to know how to plug those parts in to the equation correctly. So we have now the equation for the tangent line, but it's in point-slope form. We'd like to have this in slope-intercept form. We are asked to do that, so we have to convert to slope-intercept form. We do that by solving for y. So that's our equation for the tangent line in slope-intercept form. Now let's go back up and see what question F is. Question F is to illustrate the results for B, C, D, and E on a given graph. So let's have a quick look at those results. In B, we found that f prime parentheses 3 is 0. In C, we found that f prime parentheses 0 is -9. In D, we found that the points on the graph with horizontal tangent lines were the points with x equals -1 and x equals 3. And finally, in question E, we found an equation for this tangent line. So let's go illustrate all of those on the graph. The result for B was that f prime parentheses 3 equals 0. That corresponds to the fact that the graph has a horizontal tangent line at x equals 3. The result for question C was that f prime parentheses 0 equals -9. That tells us that the line that's tangent to the graph at x equals 0 has a slope of -9. So we have to draw that tangent line and label its slope. So that corresponds to the result from C. F prime parentheses 0 is -9. In question D, we found that f prime was equal to 0 at x equals 1 and x equals 3. In other words, those are the places where the tangent line is going to be horizontal. So we illustrate that by drawing in those horizontal tangent lines. Now question E was about the line that's tangent to the graph at x equals 2. That's this tangent line. Now we found that its equation was y equals -9x plus 7. And we also found that the xy coordinates at the point of tangency were 2, -11. We could do a better job of illustrating that tangent line. For one thing, we know its slope, we might as well label that, and we know its y-intercept. Its y-intercept is going to be at the point 0, 7. So that blue line is the line that's tangent to the graph of f at x equals 2. That's the end of example 2. Let's go on to the next example. Example 3. An object is moving along a straight track with position function f of x equals this polynomial, where x is the time in seconds, and f of x is the position in meters at time x. So question A is find the velocity function. So the velocity function we abbreviate by the letter v, and we have to recall what velocity means. Let's go up and look again at our discussion of review of the idea of velocity. So the instantaneous velocity at a certain time means f prime at that time. So the velocity function is f prime parentheses x. So the velocity function is a function of x, and it's f prime parentheses x, the way we get it. So that means we're going to do the derivative of 2x cubed minus 21x squared plus 60x. So let's do this in stages. We'll use the sum and constant multiple rule. And then we'll use the power rule. First, we'll copy down the things that don't change. And then in those parentheses, we put the derivatives that we get from using the power rule. Here we have a power function with n equals 3. So when we write down the right side of the power rule, we write down the n times x raised to the n minus 1. So 3 times x to the 3 minus 1. In the next term, we have an n equals 2. So we're going to write down the right side of the power rule here using n equals 2. So that's going to be 2 times x to the 2 minus 1. And here we have a power function with n equals 1. So we're going to write down the right side of the power rule with n equals 1. Simplify. So there's our velocity function. v of x equals 6x squared minus 42x plus 60. Question B says, find the velocity at time x equals 3. Let's do that on the next page. So the symbol for the velocity at time x equals 3 is just v parentheses 3. V is the velocity function, so we're going to compute v parentheses 3. And that just means that we are going to compute f prime parentheses 3, because again, the velocity function is f prime. And this symbol means to substitute x equals 3 into the formula for f prime of x. So our formula for f prime of x is 6x squared minus 42x plus 60, so we have to substitute x equals 3 into that. So the velocity at time 3 is the number negative 12. Now with units, that would be minus 12 meters per second. That means that the object is moving backwards at time 3. It's moving backwards with a speed of 12 meters per second. Let's go back and see the question for part C. Find the velocity at time x equals 0. So we have to find velocity at time 0. That means v parentheses 0. And that symbol just means that we substitute x equals 0 into the formula for f prime of x. So the result is that the velocity at time 0 is 60. Let's go up and see what our next question is. That should have been C. Question D is, at what times is the velocity equal to 0? To find that, we have to set the velocity equal to 0 and solve for x. So I'm going to turn that around. I'm going to say 0 equals the velocity, which is equal to f prime of x, which is equal to that polynomial function. So we're going to solve this by factoring. So we see that the solutions to this equation are x equals 2 and x equals 5. So those are the times when the velocity is 0. So those are our 3 results to questions B, C, and D. In question E, we're supposed to illustrate those on a given graph. Here's a given graph of the function. So we're doing question E now. Now remember that this function f of x is the position at time x. Now let's recall our results. For question B, we found that the velocity at time 3 was negative 12. That is f prime parentheses 3 equals negative 12. We illustrate that by finding the place on the graph where x equals 3, drawing the tangent line, and labeling its slope. For question C, we found that f prime parentheses 0 was 60. That means the velocity at time 0 was 60. We illustrate that by putting a tangent line on the graph at x equals 0 and labeling it with its slope. And in question D, we found that the velocity was 0 at times 2 and 5. But remember that the velocity function is the derivative function. So to say that the velocity is 0 at time 2 means that f prime parentheses 2 equals 0. We illustrate that by drawing a tangent line at time 2 and having it labeled with its slope, which is going to be m equals 0. And also at time 5. Think about what this means. This result means that at time 0, the object was moving with a speed or velocity of 60 meters per second. This means that the object was moving with a velocity of 0. That means the object was not moving. Notice the position graph has stopped going up and is momentarily not going up or down. This result means that the object is moving with a velocity of minus 12 meters per second. In other words, the object is moving backwards. Its position is decreasing. This means that the object is standing still again at time x equals 5. That's the end of this example, and that's the end of the video. Thank you.